SwayamPrabha. Digital India. Educated India.
Hello and welcome everyone to today's lecture on the series for modeling of multiphysics systems. Today is lecture 3 and we will start by continuing our lecture 2 on vector calculus. Once we finish that, we will go on towards dimension analysis. Okay. So, in the last lecture we have talked about what are scalar fields and what are vector fields. So, scalar fields they are a function defined in all the 3 coordinate systems of a 3D space. Vector fields is defined by 3 functions and likewise the tensor field will be defined by 9 functions. We have also looked into different vector calculus operators like gradient, divergence, Laplacian, curl. Okay. So, in this lecture we will start with the basic theorems for vector calculus. So, the first theorem is the Gauss divergence theorem. It is one of the most critical and important theorem to be used. So, the Gauss divergence theorem, if you take a vector field f which is continuously differentiable in a given volume. So, let us take an arbitrary volume V which is bound by a surface S which is equals to del V. So, within this surface we have a function f which is a vector field. So, this vector field is such that the f dotted with n where n is the surface normal. So, what is f? I can draw it over here. So, we have a flux of a vector going out from a given volume. So, this volume V is bound by a piecewise continuous surface. And this f, if we take a dot product with the surface normal, that should be equals to the divergence of f integrated over the volume V. So, for this volume V, we are integrating the divergence. So, what does divergence mean? From last class, we have seen that divergence is linked to the net source or sink, that is a net outflux or influx of a given vector field. So, if f is net going outwards, then the divergence of f is positive. F is in summation is getting inwards, then the divergence is negative. So, what this relation tells us is that for a vector field f, the theorem relates the net outflux of f vector from the surface to the total source or sink in the volume. Okay. So, f dot s or f vector dot with the surface normal gives us the net outflux. If it is positive, if it is outflux, it is negative if it is influx, and likewise del dot f gives us a similar sense integrated over the volume. So, it is a conservation law. So, we can take our 2 old vectors. So, these were examples. So, the first one was our s vector. S vector, if you remember, was our spin vector. So, it was minus x2 along E1 and x1 along E2, and this was a spin vector. It was rotating in the counterclockwise direction. So, we can take this vector and we can integrate this along the normal direction to the plane. So, s vector dot with the E3 direction ds is equals to 0, right, and likewise integral of del dot s dv is equals to 0. Okay. So, for that given surface which is inbound, we can see that the net flux getting in and getting out is equals to 0. All right. So, with that in mind, we can go to our radial vector. So, our radial vector r vector was equals to x1 e1 plus x2 e2 plus x3 x3 E3. Okay, so let's draw a cube of our coordinate system E1, E2 and E3. Okay, so let's say that each side is A for this cube. So we have a cube volume. So integral over volume del dot r cap r vector into dv will be equals to 3a cube. Okay, so 1 plus 1 plus 1 is 3, integration over the volume is a cube, so 3a cube. Okay, so it is 1 along each direction. Okay, that is 3a cube. If we do the same but along the surface, so surface bound for this r vector dot with the surface normal into ds. So we will have 6 planes for a cube. Front and back, top and bottom, and left and right. So we can take double integrals from 0 to a, plus minus x3 along dx1 dx2 plus integral 0 to a plus minus x2 along dx1 dx3 dx3. All right. So if we take this integral, we can find out it is x1 into x2 into x3 along all 3. We have the top plane and the bottom plane. Once we integrate all of them, we can find this comes out to be 3a cube. Okay, so dx1 x2 is this back and front plane, x2 x3 will be these 2 planes, and x1 x3 that is this bottom and the top plane. Okay, so that gives us a sense of the net outflux. So this radial vector will be pointing all out in all the 3 dimensions. This is your r vector. And we have seen r vector in the last lecture, and we can see that the r vector is moving outwards, or is a net outflux. Okay. Now, so what did we get out of the divergence theorem is that it related this flux concept or the outflux concept to the source and sink term. Okay, it is one of the most useful theorems. Gauss divergence theorems finds its use in electrostatics. So some applications. So we can find it in the Gauss law of electrostatics. So what we can get here is that the integral over volume, I am not writing 3 integrals every time, rho over epsilon naught into dv is equals to integral over surface E vector dot with the surface normal into ds. So the net electric field on the surface of a given body integrated over the surface is equals to the charge density over epsilon naught. Epsilon naught is permittivity of the medium. Well, it's permittivity of free space. If we multiply with epsilon r, it's permittivity of medium integrated over the volume. So that all the charge accumulated in the volume creates the electric field on the surface. Okay, so if I draw a small example, so we can have all the charges being accumulated in the volume. This is rho, and then we have the electric field on the surface E vector. Okay, so we can then modify this as an integration over volume del vector dot E vector into dv. We can bring both terms to the left hand side. So integration over volume rho over epsilon naught minus del vector dot E vector into dv equals to 0. Now, in this concept, either we can have the integrand to be 0, or we can have the volume to be 0. So volume to be 0 is arbitrary. We really cannot have that. It's just one case, right? The other thing will be that the thing under the integration can be 0, and that is for an arbitrary volume. So with this in mind, for an arbitrary volume, rho over epsilon naught minus del dot E goes to 0, or del dot E to rho over epsilon naught. Okay. So, this is our differential form of the Gauss law. Okay, the first one was the integral form. So, this one was the integral form. The divergence theorem is also applicable for heat diffusion equations. I will not go over that because we will go in depth when we talk about heat transfer and mass transfer. The next theorem that we will go on is the Green's theorem. So, consider a 2D space. We have a smooth continuous vector field F vector, where F vector is m E x plus n E y. M and n are both functions in x1 and x2. So, m is x comma y, and n is also x comma y. So, we have two functions m and n that defined a vector field F in a piecewise continuous surface. So, we have a circumference C along which is equals to del S, which is binding a surface S in a 2D plane. So, this needs to be 2D for Green's theorem. So, what the Green's theorem states is that the cyclic integral over the circumference C is equals to del S m into dx plus n into dy is equals to integral over the entire surface, the partial derivative of n with respect to x, partial derivative of m with respect to y, dx into dy. Okay. So, what it signifies or what the Green's theorem signifies that the sum of all the microscopic circulations which is inside a bounded surface S is equals to the macroscopic circulation. If we have a 2D surface and we have these small vortices and rotations going on to this 2D plane, the summation of all these small rotations, so counterclockwise and clockwise will cancel each other out, and sum of all of these small vortices together gives us a net circulation in that bounded region or the bounded surface. Okay, let us try to prove this theorem just like we tried to prove Gauss divergence. So, the proof will be, let us take again a function f vector equals to m along Ex and n along Ey. Let us take 2 points, point A and point B. We have two paths that we can go by. So, we can go from point A to B along this, and we can come back from point B to A along this path. So, we will treat each m and n functions separately. Let us start with m function. So, m function is defined along the Ex direction. So, we can take a small strip within this bounded region. This will be equals to double integral of minus del m by del y into dy, dx dy. Okay. So, what we have is circular integral of m along dx is equals to double integral of minus del m by del y to dx dy. Okay. Let us try to prove this term first. Okay. So, we integrate minus del m by del y with respect to y first. So, this is the first integration. Okay. Let me write down a few terms. The lower plane is integral m dy, the top one is integral minus m dy. The bottom function or the path it follows from A to B, y is equals to some small f x, and the top path it follows, y is equals to small g x. Oh, the other way around, I am sorry. The top one is f x and the bottom one is g x. Okay. So, the first integration, we are doing integration from the bottom plane, that is g, to the top plane, that is f, top line or the curve of minus del m by del y into dy. Okay. So, this integration will give us minus m of x of fx plus m x of gx. Okay. So, the bottom one is g, the top one is f. We have a minus sign, so the signs will flip, or the integration will flip. It will go from f to g rather than from g to f, and we will get this as an output. Okay. Then we integrate it again, the second integration. Is with respect to x. So, what we will have, so our circular integral of m along the path dx will be equals to integration a. So, we are going from a to b, let us go back to our figure quickly. So, we are going from a to b, and we are following from a to b this arrow, and then we are coming back from b to a. So, if that is the case, then we will integrate this first the top one of m of x comma y dx plus integral the bottom m of x comma y into dx. Okay, so, the top one we will integrate from b to a, we are coming back. So, m of x comma f, the path is f dx, this integral we are going from the bottom is from a to b. So, we will integrate from a to b m x comma g dx. Okay. We can flip this sign, this will be minus if integrated all from a to b of m of x comma f dx plus m of x comma g dx. Now, if we see the last expression, this expression was equals to integration from g to f minus del m by del y dy. So, we can substitute. So, substituting of minus m x f plus m x g is equals to integral minus del m by del y dy from g to f, if I am not very wrong, yes, from g to f. We will substitute. So, we will have our cyclic integral of m dx is equals to integration from a to b, integration from g to f minus del m by del y dy. So, this is our first case. So, let us name it 1, first equation. Now, let us take the n function. Let us draw our figure again from point A to point P. We have two paths. Okay. So, we go from A to B from the bottom line, and we come back from B to A by the top line. In this case, n is along the EY direction. So, our integration will be along this this dy strip. So, this is double integral of del n by del y dx dy. Okay. Now, in this strip we will flip the functions. So, this is x is equals to f of y, as x is equals to g of y. This is integral of n dy, this is integral of minus n dy. Okay. So, we will treat n similar to m. So, we want to get cyclic integral of n dc should be equals to double integral of del n by del x. I am typing this wrong. It should also be x dx dy. Okay, again let us start with this expression. So, we integrate del n by del x with respect to x. That is the first step, just like last time. So, we have integration, in this case x is going from g of y to f of y del n by del x dx. This is equals to n f of y, that is our x, into y minus n g of y comma y. All right. then we integrate again with respect to y. So, we will have integration from a to b, integration from g to f, del n by del x dx dy, and this will be equals to integration of this function from a to b n of f comma y dy minus integration of a to b n of g comma y dy. Okay. Now, we can flip this sign, we can make this plus and we can flip the sign. So, integral a to b n of f y dy plus integral b to a n of g comma y dy. Now, let us quickly go back to our figure. So, we have seen that from a to b the path is f and from b to a the path is g. That is our integration. From a to b it is f and from b to a it is g. This is our cyclic integral of the n along C. All right. So, now we can add the two. This is our equation 2. So, we can add 1 and 2. So, we will have over C. So, cyclic integral over the surface m, this is dy, m dx plus n dy. Let me go back quickly, one slide. Yes, that's correct. Equals to integral 2 times over the surface S. We have del n by del x minus del m by del y dx dy. Okay, and that proves our Green's theorem. So, this is our Green's theorem. Okay. So, just quickly going over what we talked in this Green's theorem is that we have this vector field f having m and n as the two components or the two functions along x and y. We first did m, integrated it along this del m by del y minus del m by del y, and we found out what these values are, and then we integrated again with respect to x. So, we got equation 1. Likewise, we took the function n, we did the first integration, okay, this is instead of c, this should be del y. We did the first integration with respect to x of the del n by del x term, and then we integrated with respect to y. We added the sums together and we found out that it matches, the output that we get is the Green's theorem. Okay. Stokes' theorem is the, we can say, the 3D counterpart of Green's theorem. So, we have the same vector field function f, and the function f is a smooth continuous function. These functions for the divergence theorem, for the Green's theorem and Stokes' theorem should be continuous to the first order partial derivative. So, let me write it down. So, f vector for our Gauss, Green and Stokes theorem needs to be smooth and continuous up to first order partial derivative along x, y, z. All right. So, taking the same f vector, now instead of a 2D surface, we have a 3D surface. So, we have 3 dimensions. Let us take a 3D, 3 planes of a pyramid, something say we have a pyramid like this. So, we have this plane, this is one plane, this is another plane, there is a back plane and of this bound, and then there is a bottom plane which is acting. So, if we have a 3D surface which is bound by a circumference c, that is del s, then this Green's theorem can be taken up to Stokes' theorem, in which the cyclic integral in the counterclockwise direction, again these are all counterclockwise. in the counterclockwise direction, f vector dotted with the c, that is the circumference, is equals to the surface integral of the curl of f vector dotted with the surface normal. Okay, so let's write it down again. So c is equals to f vector dot dc vector is equals to del cross f, that is a curl of f dot with n cap s ds. If you want to write it in 2D, then say f vector is equals to m along ex and n along ey. Then this is equals to cyclic integral is m dx plus n dy, which is equals to our surface integral. In this case, f the curl of f will be in the E3 direction, and that is the normal direction. So, the E3 direction, the curl is del n by del x minus del m by del y, which is del cross f is equals to del n by del x minus del m by del y along the Ez direction or the E3 direction. So, dotted with the surface normal is that into ds. Okay, so that is our Green's theorem. So, Stokes theorem is just scale up or just a one dimensional up from the Green's theorem. Okay, so we have certain applications of this. First of all, what is a gradient field? So, a gradient field is irrotational. So, which means that del cross f for a given field is 0. In that case, which means that the integral over bound f dot with r or c is equals to 0. Okay, so that is a gradient field. For example, r vector, our position vector r vector is a gradient field. So, let us just write this c instead of r, is a gradient field, which means that del cross r is equals to cyclic integral of r vector dot with a given bound surface is equals to 0. Okay, because it is flowing outwards, there is no rotational component in this case. Some applications of Stokes theorem and in terms of also of Green's theorem. The first is in fluid mechanics. So, in fluid mechanics, we can determine whether a flow is rotational or irrotational. If the del cross f vector is equals to 0, then the flow is irrotational. Okay. This can also be applied in the case of Maxwell's equation when we talk about Faraday's law. So, Faraday's law, in the integral form, we have cyclic integral C of an electric field dot with del C is equals to minus d phi b by del t. Okay, this is our magnetic flux. What is magnetic flux? Magnetic flux is integration over S b vector dot n cap S ds. This is a time varying magnetic field. Okay. So, if we substitute this back in this, we can say cyclic integral over a given C E vector dot dc is equals to, now by Stokes theorem we can write this as a surface integral del cross E into dotted with the surface normal ds is equals to minus integral over surface minus db vector by dt into ds. And what we get if we take this out for an arbitrary surface S, we will have del cross E is equals to minus dB vector by dt. This is Faraday's law. in the differential form. So, a time varying magnetic field will generate electric field, and that is related using the Stokes theorem and the magnetic flux. Okay. So, some vector calculus identities, I will not go over this in this lecture. We have already covered this when we were talking about gradient, divergence, curl and Laplacian. So, there are some distributive properties, some multiplicative properties and some quotient rules. So, we have already done these earlier. Likewise, we can have this vector calculus identities. So, a dot product of a cross product is 0, we know that. So, so the divergence of curl is 0. Likewise, the divergence of a gradient is a Laplacian, that is del dot del of f is equals to del square f. Right. Curl of the gradient is 0, so del cross del of A is 0. Curl of curl can be given by the vector triple product rule. We have done this earlier in lecture 1, vector triple product. And likewise, we can find the Laplacian out by taking this to the left and this to the right, and that is what we get in here. Okay. So, these vector calculus properties something you can memorize or something you can have a note of and use it as you are using the different vector calculus functions. Okay. With that, we end our part for the vector calculus, and we will go on towards the second segment of today's lecture, and that is the dimension analysis. So, what do you understand by dimensions and what do you understand by dimension analysis? So, whenever we as a researcher or as someone who are trying to find new phenomena of physics or chemistry in the nature, when we observe a change or a phenomena through some experiments, through some observations, we try to measure those changes. So, from a physical phenomena to a mathematical model, the linkage is these laws of physics, and these physical laws are derived based upon our observations. There are certain quantities which can derive these laws or which can describe these laws, and these are called the physical quantities. So, from a physical observation, like an experiment, to a physics law, what it links or how is linked are by physical quantities. So, these are the quantities that we can measure. For example, if you have a resistance and you have applied a voltage, you know the voltage measurement using a voltmeter, and you can measure the current that is going through the resistance. So, you can find the resistance value using Ohm's law. So, how is Ohm's law determined? In this case, the resistance was determined, voltage and current were plotted, and we could find that it was a linear line between a voltage and current. So, from that linear line, we can say that the resistance is V over I, right. So, the voltage is a measurement, is a physical quantity, current is a physical quantity, and the resistance is a physical quantity, right. So, a combination of these physical quantities derived a law, and that is our Ohm's law. So, V is equals to IR. Most experiments are done likewise, right. So, a physical quantity are the physical properties that can be defined in a physically quantifiable way. So, physically quantifiable way means that you can do an experiment, you can make an observation of a change of some parameter that can be recorded and that can be repeated. So, once you repeat these and you can get a consistent result, then you can derive some equations based upon those quantities that you are measuring. Okay. So, there are two kinds of physical quantities. The first is a base quantity and the second is a derived quantity. So, a base quantity is something that is entirely determined by physical terms, which means that there is no other way of getting those quantities like mass or time. These are absolute quantities. You can say that these are absolute quantities. There are no other quantities which can derive these or determine these. Derived quantities, on the other hand, it represents a physical phenomena based on a combination of different base quantities. For example, velocity is a combination of length and time parameter. So, length by time is velocity. So, you can use two base quantities to derive the velocity. So, velocity is a derived quantity. Okay. Now, system of units. So, how is a system of units determined or set up? So, a system of units is defined by three things. First, you have a complete set of base quantities, whatever the base quantities are required in any combination in product or summation. or based on any operation, having their base units, and these base quantities form up a set of relevant derived quantities which are incorporated in a physical equation or a physical law that gives us a system of units. A small example is that voltage is equals to I times R. Okay, in this case I is the current is a base quantity. Voltage and resistance both are derived quantities. These derived quantities and base quantities in a physical law, that is our Ohm's law, define a physical phenomenon. All right. So, from the SI system or in the SI unit system, there are 6 base quantities. These are, so we have length, it's given in meters and defined by L. We have time in second divided by T. We have mass in grams or kilograms in M, and then we have current. This is defined by amperes. You can typically use I. Then the number of moles or number of species that are present. This is given by moles or species. Mostly written as N. And then you have luminosity. This is, the unit is candela or CD. Okay. And there are different ways to write this. You can use I, or well, I is used in current. Based upon how it is used, you can define some symbol for it. But these are the 6 base quantities that are present. Now, the derived quantities, these base quantities can be combined to get derived quantities. Okay. So, let us see some examples. So, area is length square, L square, the unit is meter square. Okay. Force is mass length time minus 2, the unit is kg meter per second square. Energy is mass length square time minus 2, the unit is kg meter square per second square. And then we have charge or electric charge, that is current times time, that is ampere second. And then you can have other units as well. Power, for example, is the derivative of energy. So, that is m L square T minus 3. The usual unit is watts. We can also write as kg meter square second cube, and so on. Okay. So, these are the derived quantities that you can get. Now, what do we mean by non-dimensionalization? So, the non-dimensionalization which is also called scaling, are tools for analyzing the behavior of equations and determining which dynamics is important. Okay. So, this is the major reason why we study dimensional analysis. It is one of the quintessential factors when you are solving differential equations. And the dimensional analysis is a tool, especially when we are talking about this course, especially the modeling of multiphysics system, is that you have several equations that you are going to deal with. You will have coupled heat transfer with mass transfer, with electrochemistry, with electromagnetism. You will have current flowing through wires, leading to capacitive effects, leading to heat generation. The equations becomes so complex at times that it becomes almost impossible to set up the equations, or we do not have those resources or enough computational capability to solve these. So what we do as a researcher or as an engineer is that we try to make assumptions. So assumptions are the base of any type of mathematical modeling. How do we make these assumptions? Is that we try to simplify the equations based on those quantities that are essential and those quantities that are non-essential. For example, if we take honey versus if we take oil and we drop both of them. So in one case, which is a viscous dominant, for example, honey has a high viscosity compared to oil. In that case, the shear terms are more dominant in a Navier-Stokes equation compared to oil, in which case the convective terms might be more dominant compared to the shear terms. Right. So we make assumptions and we try to simplify down a much larger equation into smaller equations which are manageable and which we can easily solve to get almost accurate results instead of solving the entire or the whole sum equation. Okay, so how do we do these? So we start by identifying all the independent and dependent variables in an equation. So we have a governing equation and we have its boundary condition. So we will identify which variables are dependent, which are independent. We will replace each of them with a quantity that is scaled relative to the characteristic unit of measure. So we will scale them mostly to a 0 to 1 scale. For example, we have a capacitor with the gap of the capacitor is d. If you are solving the capacitance and the effect of electric field between these two plates, you will scale the x dimension by this thickness d, so that you can go from 0 to 1. So most of the scaling of these variables, dependent or independent, are done with the characteristic unit of measure of that quantity. Then we divide through by the coefficients of the highest order polynomial. So once we have normalized, we will substitute back into our differential equation, and we will then normalize each of them based on the highest order of polynomial or derivative term. Okay, once everything is brought down to one side, we will have all the constants grouped into one or two terms. We will then judiciously select a characteristic unit so that the coefficients can be reduced as much as possible to 1. Okay, so we want to get rid of all the constants. So we will select values or select variables which can accumulate these terms into one quantity. Right, these becomes our dimensional number like Reynolds number or Sherwood number or Nusselt number. Then we will rewrite our system of equations with these new dimensionless quantities. Okay, now these are the points to follow. We will try out one example to demonstrate how this is. Okay, so let's try out an example. So let's take a governing equation, take a 1D momentum diffusion, of a membrane with constant density and drag. Okay, so we are taking a membrane. Our equation is k del square u by del z square equals to c of u. Now this is a second order ODE. We will need two conditions. So two initial conditions are needed. K du by dz is equals to tau by rho and u is equals to 0. Okay, so we have these two initial conditions for our ODE. Okay, so this is our step 1, that is to define our equation and find out that u is dependent and z is independent. Okay, so u bar is equals to u over u naught and z bar is equals to z over h. Right now we do not know what u naught is. We have just scaled it with the variable u naught and we have scaled z bar with the variable h. What is h? H is the thickness or the depth term, depth of vibration of membrane. Say in this example. Okay, so now we can substitute it back into our equation. So that is step let's substitute this back. So, k u naught. So, du by dz is u naught, z square. So, it will be h square is equals to c into u naught into u bar. Okay. So, this is one. Then we will have our boundary conditions. So, k u naught over h du bar by dz bar is to tau by rho, and u naught into u bar equals to 0. The third step is that we divide with the highest order derivative of polynomial. In this case, this is the first derivative, we take it to the right hand side. So, d squared u bar by dz square, z bar square, u naught gets cancelled. So, c h squared by k into u bar, and then we will have this again, this is the highest order derivative, that is u bar by dz bar. So, du bar by dz bar equals to tau into h by rho into k into u naught, and we will have u bar is equals to 0. Okay. Now, we do not know what u naught is, right? U naught is something that is we are calculating, right? So, how will we scale this? In this case, we can make this term as 1. Okay. So, we will go to step 4. So, we can judiciously select u naught is equals to tau h by rho k. So, that this term becomes 1, and we can take a constant a, which is equals to c h square by k. Okay. So, c and k are constants, h is the depth and for the given system. So, we can take this as a constant. Then 5 is that we will substitute everything back into our differential equation, that is step 1, and what we will get is d square u bar by dz bar square equals to a into u bar. This is our equation, and our boundary conditions are du bar by dz bar equals to 1 and u bar is equals to 0. Okay. Now, we have a much simpler equation to solve. D square u bar by dz bar square equals to a u bar. We can very easily solve this second order ODE, and with these boundary conditions that we have, we can quickly establish u bar as a function of z bar. Once we have done this or solved for this, so solve for this, we can then replace u is equals to, u bar is u by u naught. What is u naught? U naught is tau h by rho k into f of z bar is z over h. So, as simple as that. Okay. So, we can get back our original u vector u. Okay. So, this is the entire process of dimensionalizing an equation. Now, a change of basis is, in the case of a variable, we can find that a change in basis or how we select these, for example, we selected u naught as tau h by rho k. How we select these variables for normalizing does not affect our analysis based upon solving the equation, right. So, the equation or the essence of the equation remains the same. So, a change in the dimensional basis keeps the law or equation intact. Okay. So, let us try one case. So, let us take a parachute, velocity, in which v velocity is a function of the d, m, g and rho, where v is the velocity, d is the diameter, okay, it is Lt minus 1, this is length, m is the mass, that is the mass of the parachute plus the person, it is m, g is the acceleration due to gravity, that is Lt minus 2, and rho is the density of air, that is ml minus 3. Okay, this is our dependent quantity, and these all of them are independent. Okay, so let us take case 1. Case 1 we are normalizing with respect to, so normalize with respect to mass and density. Okay, so what we do is we have m is equals to m, length becomes m by rho to the power of 1 by 3, time unit becomes v by g. So, if we have these, we can then normalize our variables. So, v bar is v into v divided by Lt minus 1, which is equals to, if we substitute L as m by rho to the power of 1 by 3 and time as v by g, then we will have this to be v square over g rho by m to the power of 1 by 3. Similarly, d is equals to d by L, L is m by rho. So, this is d rho by m to the power of 1 by 3. Mass normalized is 1, and same for density, because we are normalizing with mass and density. G is normalized by g by Lt minus 2, which comes out to be same as velocity v square by g rho by m to the power of 1 by 3. So, we can find that v bar is equals to g bar. We can also find that m bar equals to rho bar equals to 1. So, v bar can only be a function of d bar, because m bar and rho bar are 1, v is same as g. So, d is the only thing that is left out in this case. Okay. If that is the case, now if we renormalize, so we can say v is equals to or v bar, which is equals to v square by g rho by m to the power of 1 by 3 is equals to phi into d bar. So, v is equals to square root of g m by rho to the power of 1 by 3 phi into d bar. And what is d bar? D bar is d into rho by m to the power of 1 by 3. Okay. Now, we can define velocities by different ways. V is equals to square root gd. If it is gd, then we can say that v is equals to square root gd is equals to this term, square root g m by rho to the power of 1 by 3 phi of d bar. G gets cancelled. So, d into rho by m to the power of 1 by 3 is equals to phi into d bar. We know that this is d bar. So, d bar is equals to phi of d bar. So, our function, normalized velocity function, is equals to d bar in this case. Okay, that is the solution for this. If our normalization basis is, now if v vector is square root g m by rho d square, if this is our case, then what we get, we can substitute this square root g m by rho d square is equals to square root g m by rho to the power of 1 by 3 phi of d bar. You can do some bit of a substitution in this case. You will find phi of d bar equals to 1 by d bar square. Okay. So, in this case, we can see that our function of velocity is 1 by d bar square for this output of velocity. So, you can select different bases of getting velocity output, and you will get some function. Okay. That was our case 1. So, the case 2, we can try to normalize with respect to our length and mass. Okay. So, in this case, m is m, length is d, time is v by g. If these are the case, when we normalize this, velocity will come out to be v square over gd. This you try it out yourself. D bar equals to 1, m bar equals to 1, that is what we are normalizing against. Rho bar equals to rho d cube by m. So, velocity, now d and m are gone, velocity can only be a function of rho bar, which is equals to v square over gd. So, the velocity again, if we renormalize, is equals to square root GD into phi of rho bar. Okay. So, if we compare both cases, so the first case we had V was equals to square root, the case 1, G m by rho to the power of 1 by 3 phi d bar, and for case 2 we had velocity equals to G d phi of rho bar. Okay, these two are different bases. D bar is a different basis, rho bar is a different basis. If we compare both types of solution, what we can get is GG gets cancelled. So, phi of d bar from this case is equals to, let me put an asterisk over here because the different basis is d rho by m to the power of 1 by 3 phi of rho bar star. Okay. If we substitute d bar from the last case, so d bar was d into rho by m to the power of 1 by 3, again d into rho by m to the power of 1 by 3, and this rho bar we have found is rho into d cube over m. Okay. So, if we take this as a variable, then this is phi of some variable x bar, this is x bar is equals to x bar, capital X bar, phi of x bar cube. Okay. So, what we are finding out from this study or from this is that a change of basis does not change the function itself, but the equation remains the same, just the choice of variables are different. Why we are choosing different variables is what we will study in the next lecture. So, thank you for listening today, and we will end our session today over.